So this is the second half of chemical bonding, where we talk about molecular shapes. And then at the end, valence bond theory and molecular orbital theory. And this quote points out, no theory ever solves all the puzzles with which it is confronted at a given time. So basically, none of these theories is exactly perfect or works for every situation, but they try to cover as many bases as possible. And in some ways gives you historical, it's not a historical, but a logical step by step for like how we got to these different theories. So the first one is the simplest, VSEPR theory, which is pronounced Vesper, even though it's VSEPR, which would be like VSEPR. Valence shell electron pair repulsion theory. So this basically relies on the number of electron groups, or all of the electron groups around the central atom. They want to be as far apart as possible, because overall they've got negative charges, because it's nuclei surrounded by electrons, and so they just try to spread out. And the way that they do that in 3D space determines the geometry. Works really well for most things. We'll see at the end of this that there are exceptions, of course. But you need to be able to identify electron groups. So lone pairs, single bonds, double bonds, triple bonds, or even just a single electron, those all count as a single electron group. So double bond, yes, it's 2 bonds, yes, it's 4 electrons, only 1 electron group. Now we do treat lone pairs and then bonds a little bit differently. But if we're thinking just electron groups, we can create sort of families of shapes where the only difference is the number of bonding groups, so the number of atoms that are bound, versus the number of lone pairs, which are just pairs of electrons without another atom bound to it. So we're going to go through these pretty quick because you're going to spend a lot of time in lab going through all of these. That's the lab for this week. So I'm not going to spend too much time on it here so we can talk more about the other theories. So the first one, actually, does the book use? No. Okay, so I guess what I will add to these is there's another notation. It's called AXE notation, but the X and the E represent the number of bonding groups and the number of lone pairs. So X will be your bonding groups. It might come up later, actually. And then E is lone pairs. If we've got 2 electron groups here around the central atom and beryllium chloride, for all of these, they're based on the Lewis structures. So you make the best Lewis structure possible and then count the number of bonding groups, pairs on the central atom. So like for beryllium chloride, this is one of those weird ones where beryllium only has 2 electrons, so it doesn't need a full octet. And then because we only have 2 groups on this atom, the farthest apart they can get is on opposite sides. So under AXE geometry, this would be X2. This will just be AX2. Because there's no lone pairs on my central atom, so nothing for the E. All right, like I said, not going to spend too much time. Another version of this could be 2 double bonds on the central atom, so carbon dioxide. Again, I just, from doing them so many times, know what these Lewis structures should be. So again, you would count central atom. How many bonding groups does it have? 2. Because you count double bonds are 1 bonding group. We're not counting the number of bonds, counting the number of groups. So this whole thing counts as 1 group. This counts as another group. So this would also be AX2. The A is just, I don't know, central atom. Yeah, so the A is never going to change. It's always going to be 1. Maybe if you go to like more complex, probably inorganic chemistry, we might use that. Okay. So those are both linear. So the AX2 is always going to be linear. And there's really not much else for the AX2 because if I remove one of these and replace it with a lone pair, then it's still just linear, but now I've only got 2 groups. And the only shape you can draw with 2 points is a line. So 2 atoms is always linear. It's when we add more than 2 atoms that are more complicated. So 3 electron groups. And as you're Lab manual is going to call it the AX3 family. So 3 electron groups. So BF3 would be one example. Again, boron's one of the exceptions to the octet rule. If you draw the Lewis structure, get something like that. Say 3 bonds, 3 bonding groups, so AX3, and that's trigonal planar. And let's see here. So it's called trigonal planar because we can draw it like we'd had on the slide where it was like this, it's like a Y. But if you're to rotate this, because these all exist in 3D space, it's flat. So say all of those bonds exist in the same plane, and right now that third bond is occluded or blocked by the central atom. But I can rotate this, and it's all just flat. So that's AX3. And the maximum separation between them is 120 degrees. Now, if we switch this up a little bit, it's still trigonal planar. It would have this Lewis structure, but because we have a difference in electronegativity, the oxygen is larger, more electronegative, has more electrons. Remember, in this model, it's the electrons that are repelling each other. So over here, I've got more electrons. So what happens is that is repelling these hydrogens more than the hydrogens are repelling each other. So the hydrogens get squished a little bit closer together. The bond angle between an oxygen and a hydrogen gets a little bit wider. And we'd say that this is the bond angle. If you're doing a triangle, if you're doing the angles on a triangle, you like C, so that'd be from A to B to C. So the oxygen carbon hydrogen bond angle is larger than the expected 120 degrees. If we were to say the hydrogen carbon hydrogen bond angle would be less than. So I'm not going to ask you for specific values here, just more than or less than 120 in this case. So trigonal planar will always have a sort of base ideal geometry, ideal bond angle of 120 degrees. The groups can change that. If these are all the same, like they were on this one, it's 120. There's no one of these fluorines that's a stronger negative charge than the others. Okay, so we have a central atom in a 3-atom molecule, forms 2 double bonds, has no lone pairs. What would that geometry be? So if we think in terms of the AXE, 2 double bonds would be AX2. And then no lone pairs, linear. Huh? Oh, yeah. I think we're going to see. Sorry, it would be AX3. I did the AX3 family. Because the thing that's not on the slides here, right? Now what happens if I take one of these and I replace it with a lone pair? We'll probably get it's probably on a later slide. So if I replace one of them with a lone pair, I can actually think of an example. Sure, BH2 minus, which probably doesn't exist. So now I've got 2 bonding groups, the hydrogens, and 1 lone pair. So this would be AX2, or sometimes you might leave that subscript off of the E. Because if there is an E, then there has to be at least one. So what shape would you call it? Not this one. So this one's basically this, but I replace one with a lone pair, so it's not a line. It's bent. Yeah, so it's like taking this guy and I remove one bond, and I put a lone pair on instead. Most of the time we're talking about molecular geometries. So molecular geometry is bent. Now the electron geometry is just counting all of the groups. Electron geometry would be trigonal planar. And if I click this option, just show the stuff that has mass. I don't know, you can think of lone pairs as they're like ghosts. Right? They don't have any matter. They don't actually take up any space. But the other atoms that are bound to the central atom, they're afraid of it, so they don't want to go near it. So they get away from the ghost. Yeah, so it'd be AX2E. And really right now what we're doing is we're setting up the basic shapes though. You can have two groups, so the AX2, that's a family. I mean, there's only one in that one. The AX3 has another option. The AX4, 4 electron groups, they get harder to visualize because you might expect we went from 180, I put one on, then they split into thirds. If I put a fourth one on, you might think they'll split into quarters. So you might get something, might be thinking something like this. That would be true if it was flat. But there's more space that we can use because this bond angle is 90 degrees. But if I move into 3 dimensions, we can actually get up to 109.5 degrees between our different bound atoms. Oh, that's right. That's why I have balloons in my office. To do something like this. So if you take 3 balloons and put them together, you get something like this. If you add a 4th balloon to that, then these 3 balloons have to go down for that 4th balloon to fit on top. Actually, that's what you get rid of a lone pair. So here's my, oops, 3 of them. These are fun. I can actually just grab one and move it around. You can see the others always move to get away from it. Anyways, so that's flat. But now if I add a 4th group, it fits on top. Forces these other ones to go down, because if I try to make it flat, they do not want to be flat. There's more room in the 3-dimensional shape tetrahedral. There. So the tetrahedral is called a tetrahedral because it's got 4 points and 4 sides. So this is the tetrahedral geometry. It's a tetrahedron. Has a bond angle of 109.5 degrees. So just as one example, molecule methane, CH4. It's got 4 groups. Again, this is the AX4. So just like with AX3, so AX3, I could remove one of those, swap it out for a lone pair. Here, I can do the same thing. I can take one of these hydrogens and swap it out for a lone pair, and that'll give me a different molecular geometry. And I can swap another one out, and that'll give me another molecular geometry, which I'm pretty sure we'll see here pretty soon. For hydrogen cyanide, hydrocyanic acid, what would you expect the geometry to be, maybe? How many bonding groups do I have? 2. All right, triple bonds count as 1. So 1 bonding group, 2 bonding groups. So it'd be AX2. And then there's nothing else on the central atom, even though this nitrogen has a lone pair. We don't count that. We're just concerned about the central atom. So AX2 is linear. All right, now we get to move beyond Chem 20, because those are all the basic shapes in Chem 20. And I think we'll come back and do, in the slides, we'll swap out all of those other shapes. So now we're going to AX5. 5 groups. So in 5 groups, we now have basically 1 on top, 1 on bottom, and then this sort of trigonal planar configuration in the middle. What you end up with is 2 pyramids. So it's called trigonal bipyramidal. You get 2 pyramids there. And again, all moving apart here so that we get the maximum amount of space possible. The bond angles here are actually a combination. So there's the equatorial chlorines. So if you think of this as the Earth, we got a South Pole, North Pole. The equator is the ones on the outside. These are 120 degrees apart. They're only 90 degrees apart from the axial chlorines. So you can also think of it like a wheel. Yeah, again, we're going to spend a bunch of time making models in lab. So the next one's AX6. This is the octahedral, and now finally we are limited to everything only having 90 degrees. So all of your bond angles are 90 degrees now. So if you had to guess, there's really only 3 numbers. There's 90 degrees, there's 120 degrees, and there's 109.5 degrees. And it's going to be one of those greater than or less than. 6, octahedral. Hold on. Yeah, okay, cool. We're going to come back and do lone pairs. All right, so Molecular geometry of CCl4. So for all of these, the first thing is always a Lewis structure. So that's the basic shape. And then we could add up all of those. So 4 chlorines is 7 times 4. So that's 28 plus another 4, 32. And then I used 8. So that's 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is that a good Lewis structure? Yeah. We've got octets, and actually everything also has a formal charge of 0. Now, how do we figure out what the basic shape is? Yeah, so we're going to do the AXE. How many bonding groups do I have? 4. How many lone pairs do I have on the central atom? 0. So each of the chlorines has 3 lone pairs, but again, we don't care about those for the overall shape. We only care about lone pairs that might be on the central atom. So if there aren't any lone pairs on the central atom, we don't write them down. So AX4 is what shape? Tetrahedral. And what bond angle would that have? 109.5. Okay. Is this going to be exactly 109.5 on this molecule? Yeah, because all of my groups are the same. If I swap some of those out for hydrogens, so let's say I did still AX4, still tetrahedral, but now what would my, let's say, hydrogen carbon hydrogen bond angle be? It would be less than 109.5 because the chlorine's more electronegative. It's also larger. So the hydrogens will get closer together. So this will be less than 109.5. And the hydrogen carbon, so hydrogen carbon chlorine bond would be larger than 109. Cool. So the basic shapes are all the AX2, AX3, AX4, AX5, AX6. So there's 5 of them because AX1 isn't a thing. It is, but it's always a line because it's only 2 atoms. When we add electrons, again, this is, we saw some of them because I did a few, but we're replacing an X, a bonding group, with a lone pair. And the effect on the electron geometry, so just all electron groups, bonding groups, lone pairs, doesn't change anything. It's the same geometry. The only thing that we're changing is the arrangement of the atoms, or the molecular geometry. And those have, in most cases, different names. So 4 electron groups with a lone pair. So what would be the AXE notation for this molecule? Was that? Yeah, AX3, E1, 3 bonding groups, 1 lone pair. And then the total of X plus E is going to be 4. So basic shape is a tetrahedral. So electron geometry is a tetrahedral. But now if we're looking at the molecular geometry, we're only counting the arrangement of atoms. So we ignore the fact that lone pair is there. We don't quite get a tetrahedral, but we get this sort of short pyramid. So that'll be trigonal pyramidal. You can see that on here. So I got the tetrahedral, remove a bonding group, add a lone pair, and you get a little pyramid. So we're ignoring that. So what happens if I take off another bonding group and replace it with a lone pair? Oh, I can't do it when it's like that. Okay. So there's multiple ways, thought of phrasing there. There's multiple ways to get a bent molecular geometry. This is just one of them. The other one would be, I guess we didn't see that. We saw it earlier, but if I only have 1 lone pair that looks almost the same. So I put 2 lone pairs on here, I can hide them, I can still delete them. All right, so we got that, and if I take 1 off, it changes a little bit, but it's still the same basic shape. So the bent shape is always going to be when we get 3 atoms. AX2, E1 would be bent, E2 would be bent, E3 would be bent, I can keep adding lone pairs, but the geometry essentially between those two, oh, I take that back. I forgot about this one. We'll see why. Yeah, so just the last one. Last two. Anyways, AX3E is the trigonal pyramidal. Just looking at the atoms. Oh, and then lone pairs have the same effect as like a larger atom or a more electronegative atom, and actually even more. So they'll push the hydrogens closer together. And again, the hydrogens are afraid of the lone pair ghost, so they get away from it. It looks like a ghost too. Yeah. You'll get, whenever you have a lone pair on there, the bonding group will have a smaller angle than they normally would. So this is, actually, what would be the AXE notation for this one? They're all the same, just one's hiding them. So for water. So on a Lewis structure, it would look like this. So there's two bonding groups, and then there's two lone pairs. And now before we saw 107 for the trigonal pyramidal, now it's down to 104.5 because we got two lone pairs. And so the hydrogens will get even closer together. So it's another way to get the bent molecular geometry. So this will become actually even more important later. So relative repulsion of electron groups, this is the reason that we get smaller bond angles between the hydrogens as we add lone pairs. Because the lone pair repulsion is the strongest, the lone pair bonding group is stronger than the bonding. So if I have lone pairs on there, those interactions are less favorable than between bonding groups. So these molecular geometries, these ones don't matter so much. I mean, we see this angle decrease, but when we start adding more lone pairs, especially for AX5 and AX6, we've got different options for where we can put lone pairs, and that changes depending on this, to minimize lone pair bonding interactions. So if you have an option, you want to minimize that. Actually, here, this, it's like for water, which is the only one we've seen so far that has a lone pair. All right, so is there any way that I can make it so the lone pairs aren't next to each other? I can try and, I meant to grab a lone pair. Give me a lone pair. No? Oh, there we go. So I can try and move this to not be next to the other lone pair, but because of the way the geometry is, there's not a space farther away. It's always going to be next to it. Because each of these, so like this lone pair that's on the front here, is next to the other three groups. So each group is always going to be adjacent to the other three groups. Yeah, you want as few of those as possible. On these shapes, it's unavoidable that you have at least, on the water, it's unavoidable to have at least one. Okay, so what molecular geometry of a molecule whose central, or what is the geometry whose central atom has three bonding groups and one lone pair? The molecular geometry? AX3E1. So the electron geometry would be tetrahedral. But if we're just thinking about the atoms, it's a little pyramid. So it's trigonal pyramidal. So it's not going to be trigonal planar because they're going to be in this tetrahedral, but one of those is replaced with a lone pair. Bless you. Okay, so 5 electron groups, lone pairs. This one, we've got AX4, E1. And this is what I was talking about, the number of lone pair interactions or lone pair bonding group interactions. We want to minimize it because here we've got 2 different bond angles. Between the axial and the equatorial, that's 90 degrees. But between 2 equatorials, it's 120 degrees. So if I put the lone pair here, it's got 3 90-degree lone pair bonding group interactions. But if I put it on the side, now it's only got 2 90-degree lone pair bonding interactions, put the top one and the bottom one, and then the bond angle to the sides is going to be 120. Because it can get more space, we could reduce the number of lone pair bonding pair repulsions. The molecular geometry ends up being seesaw. So you can see that on here. So I can try and move this and put it on top, and the other ones will always move so that we've got the smallest number of lone pair bonding group interactions. So if I take off another bonding group and I put another lone pair on, where's that lone pair going to go? Would I replace one of these on the side, or would I replace the one on top? Huh? It's already bipyramid. Yeah. So by putting it on, no, wait, no, you're thinking of square planar. So on this one, yeah, so here I have 120 to here, 90 to here. If I replace this one on top, then it'll be 90 to the other lone pair. So the lone pair interaction is the worst. So definitely have to not have a 90-degree lone pair, right? I could put them on opposite ends, but then I would have 3 lone pair bonding pair interactions for each. So if I did this, right, so this has 3 lone pair bonding pair. This one would have 3 lone pair bonding pair that are all 90 degrees. But if I do this and put them both in equatorial positions, now this one only has, now each of these only has 2 90-degree lone pair bonding pair. There's the lone pair, which is 120 degrees. So it ends up being a little bit of a compromise between the two. We still have the lone pairs closer together than they really have to be, because they could be 180. But we strike a balance between that and the bonding pair lone pair interactions. Like the, wait, sorry, say again? I think it would still be 120. Oh no, it'd be a little less than 9 or 120. So that would be less than 120, because this would want to be more than 120. These ones would probably be a little bit less than 90, because this fluorine could move closer to this fluorine. That's tricky to think about. So this is the AX3E2. And so if we just look at the molecular geometry, just the atoms, it makes a T, which is why it's called a T shape. I wonder, does this simulation have, no. Oh yeah, okay. Perfect. So this is the SF4. Here are the bond angles. Oh, that's SF4. Is there CLF3? Oh, okay. It doesn't have the lone pair angles. Let me arrange that like it was. So I swap between this and this. So this fluorine group does get pushed farther away from the 2 lone pairs, so it's closer to this fluorine, meaning this angle becomes less than 190. Oh, sorry, I wrote less than 190 over there. That would be greater than 190, or greater than 90. Over here, this angle would be less than 90. You can see too that both sides are getting pushed over. I thought you'd be able to see this too, but not really, because this, it doesn't show it, but I would expect this angle to be less than 120 and this one to be more than 120. Oh, you can't see the mouse. this angle to be more than or less than 120, because the lone pairs are repelling against each other. This angle would be more than 120. As soon as I go to 3 lone pairs, yeah, we're still in this 5 electron group family, so the AX5, or AX5 family. So this would be AX2E3. And again, we get the linear shape because we want to minimize the interactions between our lone pairs. And so the farthest apart that the lone pairs can get is in this equatorial position, so they'd have 120 degrees between each of them. We haven't talked a ton about polarity, but would you expect this molecule to be polar or nonpolar? It's symmetrical, so it'd be nonpolar. So yeah, nonpolar means that there's poles. There's one pole that's more positive, there's one pole that's more negative. Since this is perfectly symmetrical, then it's nonpolar. Whereas if I go back up to this one, polar or nonpolar? Polar, right? Because these lone pairs are on one side, those are really negative. I've got atoms on the other side, so that side's going to be more positive. So it's asymmetric. But no matter how we look at this one, it's going to be symmetric. So ends up being nonpolar. So 6 electron groups with lone pairs. Again, we're just doing the same thing where this would be AX5. The base shape is going to be the octahedral. And now the octahedral is a little bit different because all of my lone pairs, or sorry, I guess all of my bond angles in an octahedral are 90 degrees. So axial versus equatorial doesn't really matter. So if I put one lone pair on, I just replace one of these, and you get a square pyramidal. Just like how we took the tetrahedral, if you replace one of those, you get a trigonal pyramidal. Now you've got a square pyramid. More like the Great Pyramid. Yes, you might have seen it, but so what happens if where would I put my next lone pair? Which fluorine would I replace? Why the top one? It's the farthest away from the other one. So if I put it on the side here, that would put it adjacent to or next to the other lone pair. In this case, when I replace one of them, it goes on top or on the opposite side of the previous lone pair, E2. You get, again, electron geometry is octahedral. And since I've got these 2 lone pairs on opposite sides, that causes the fluorines here to all spread out in a X. And so this is where you get square planar. And then would this be polar or nonpolar? Is one side going to be more negative than the other? I've got a lone pair here on top. That's going to cancel out basically anything that the lone pair on the bottom's doing. So that axis doesn't do anything. And then all the other axes, it's just fluorine. So that's going to be nonpolar. I'm surprised we didn't do... What would happen if I added... Might not even exist. But if we go to 3 lone pairs, where would the third lone pair go? They're all going to have about the same bond angle, so it would just replace any of these, and you would get back to a T shape. Then you replace one more, then it's linear again. But here's the table of all of them. And they're sorted based on first electron groups, and then starting with all bonding groups, you replace 1, replace 2, replace 3. And so you get a lot of these shapes. And the basic families that we were talking about are pretty much for the electron geometries. So the first one is just 2 groups, is always going to be linear. 3 for the electron geometry is going to be trigonal planar. Then depending on how many of those groups are lone pairs, could be trigonal planar or bent. And then the tetrahedral family has the tetrahedral, trigonal pyramidal, and then another bent. Trigonal bipyramidal is more up to 5 groups. Right, so these are all trigonal bipyramidal. But depending on how many lone pairs there are, we can get the seesaw, T-shaped, or even back to linear. And then for the octahedral, square pyramidal and square planar are the other ones in that sort of family. Yeah. Oh, yes. Yeah, that's just a way of drawing a three-dimensional picture on a flat piece of paper. Yeah. So like you could draw all of these in that manner. So like this SF6, you draw sulfur and then do these fluorines are going back. These fluorines are coming out. Draw a better triangle. And then any just straight line means it's in the plane of the page. Yeah. Solid wedge is coming out. Dashed line means it's behind. I don't know if it's something I learned from video games or what, but just like the dashed line makes sense that it's behind. Saying that it's going behind this thing. So if I draw a box and I draw a line, then this part is hidden and then that continues on. So that's the idea with the dash, at least in my mind. So in terms of AXE notation, no. But to draw these shapes, especially things, for any of the 3D ones really, it would be best to draw it like this, with those dashes and wedges. Okay, so imagine that we've got this molecule then with 6 electron groups. It's confined to 2 dimensions. So it is flat. It's not 3D. It's not any of the shapes that we've seen. But if 2 of the 6 groups are lone pairs, where would be the best place to put the lone pairs? Why 1 and 4? Farthest away. Because you do, yeah, 1 and 3. Like that's farther away than 1 and 2, but not as far away as 1 and 4. So just as far apart as possible. So the whole thing for VSEPR theory is the atoms are moving as far apart as possible. So if you're good at visualizing that in your head, then you can just do it in your head and you don't have to memorize the different names or really the names. It's really the names that come out of the like AXE notation. So determined by the number of electron groups, and then you get the number of electron groups from the Lewis structure. So this is why it's important to get the correct number of bonds or lone pairs on the central atom, because that can drastically change the shape. And then bond angles can vary because multiple bonds or lone pairs are either bulkier, take up more space, or they're more repulsive. And so we want to minimize those repulsions, and so they get a little more space. All right. Oh yeah, one more. So which statement is always true? Yeah. So it's not just bonding electron groups. It's not just non-bonding electron groups. It's the 2 of those combined. Because if we have a combination of lone pairs, bonding pairs, we get different geometries because the lone pairs want to stay away from lone pairs. And the atoms, bonding pairs, want to stay away from lone pairs. So really, it's the most inclusive one is going to be true all the time. We're not going to do the practice because that's what the lab is. We'll talk about the other bonding theories. So you'll get plenty of practice predicting and drawing those out. So this is what I was actually just showed, that if you're representing it on paper, instead of having to be an artist, all you have to do is draw solid wedges or hatched wedges. And the hatched wedge doesn't need to be as precise. The solid wedge should look like a triangle. But this is how we show something going into the page or coming out of the page while still drawing it in a 2-dimensional form. So for larger molecules, you determine the shape around each of the interior atoms, and then the combination of those is what makes the shape of the whole molecule. I'm not going to make you do this. But for something like this one, we could say like the nitrogen, we could do the whole Lewis structure for the molecule that you should be able to do. And then the shape around the nitrogen is going to be based on the number of lone pairs, the number of bonding groups that nitrogen has. So nitrogen here would be AX3E1. And so 4 electron groups, 1 lone pair, that means it's trigonal pyramidal. So we would expect that the bonds around nitrogen would be configured in a trigonal pyramidal. And you just got to go through each and ignore the other parts. So like for this carbon, you would ignore that this exists, but keep the fact that there's a bond there. And then over here, you would ignore the other half of the molecule and say, okay, that's just 4 bonding groups. So that would be tetrahedral. And then we move to the next molecule, or the next, not molecule, but the next interior atom, say carbon. How many bonding groups does it have? 3. Does it have any lone pairs? Nope. So what would its shape be? Trigonal planar. So we say, okay, that one's trigonal planar, and then we can move on to the next one. So we go to oxygen. Say that oxygen's got 2 bonding groups, 2 lone pairs. So it would be bent. So when you're looking at larger molecules, you just break it up into the geometries around central atoms. Okay. I want to talk about polarity because that's going to be in lab. Or actually, no, actually, I think the polarity part's not. It's just the shapes. But I want to talk about polarity because we want to move forward, and we need it to talk about intermolecular forces. If you've got a simple molecule that's just 2 atoms, then the only thing you need to know is the net dipole moment between those 2 atoms. So you could use the electronegativity, use the difference in electronegativity, and say one is between whatever the values were. It's like 0.4 to 2, or yeah, 0.4 to 2. So that means there's going to be uneven sharing, so a polar covalent bond. And as long as this is a polar covalent bond, it's a polar molecule. As soon as you get larger molecules, you have to consider the dipole moments of all of the bonds together or the presence of lone pairs when determining if it's going to be polar. And the biggest thing that you're looking for, again, is asymmetry. It's like I asked the question for some of the molecules that we saw, is this going to be polar? Is this going to be nonpolar? If it's asymmetric, then you should check for polarity. If it's completely symmetric, then it's not going to be polar. Something like carbon dioxide. The carbon-oxygen bond is polar, but because I've got them on opposite sides, this is a linear molecule. Their dipole moment can be represented as a vector. So this arrow here. So the tail is the positive end and the arrowhead is the negative end. Right, so the size of this arrow and the size of this arrow and their direction are exactly matching each other in opposite directions. So if I was to add those up, and we could like put a pretend, make up a value, so call this -1, call this +1. If I add those 2 together, I end up with a 0 net dipole moment. And we'll give you some tricks for doing this faster than actually doing the vectors, but look at these first. So we look at water. Now, is water symmetric along every axis? If I cut it straight down the middle, that's symmetric. But if I cut the oxygen like this, then clearly I've got hydrogens down here, but nothing on the other side, except lone pairs. But if we're just considering the bonds here, and not the fact that there's 2 lone pairs out there also, we can look at these vectors for the hydrogens, each of the hydrogen-oxygen bonds, and we can break this up into the components. So there's going to be some upward component, and there's going to be some component to the right for that left hydrogen. Bless you. And then for this left one, there's going to be some component to the left, and then some component that goes up. So those are the components of the vectors. Now, if these were perfectly opposite, they'd cancel each other out. But I've got these 2 arrows that are going in the same direction. So in essence, when I add those together, it's like taking this one and stacking it on top of the other. And so the net effect of that is there's this large arrow going up. But if I take my other 2 vectors, I'm going to draw it over here. What's the net effect of those two vectors? They cancel out, right? If I move one to the left and then move back one to the right, back where I started, so these two vectors are in opposite directions and they would cancel, whereas this one would be 2 times in that direction. So for the net dipole moment of water, there's obviously a negative going up and then there's a positive on the other side. So when you're using these vectors, you don't necessarily need to come up with the exact vectors. If it's the same molecule or if it's the same atom, like these hydrogen-oxygen bonds, I probably didn't need to do this with the vectors. I can see that they're both pointing up. They're not going to cancel out. So that means there's going to be a dipole moment. So the Lewis structure determines the molecular geometry, so you need that first. And then you determine if there are polar bonds. If there aren't even polar bonds, then it's not going to be polar. And then you determine if the polar bonds add together to form a net dipole moment. If all your vectors sum to 0, so you don't have any that are adding to each other, they're all just canceling out, then it's nonpolar. If there is a net vector, the molecule is polar. And that's really probably the best way to do it. But for a lot of things, you can use a shortcut. Actually, I thought it was going to be next. We'll come back and look at it through the lens of both of these. So a molecular is nonpolar if both conditions are true. There are uneven lone pairs on the central atom. That's a typo. There are even lone pairs on the central atom. And all of the atoms bonded to the central atom are the same, or have the same electronegativity. So here. So this is an example of even lone pairs. So not that the number of lone pairs is even, but that they all cancel each other out. Or if I did this one, the square planar that we looked at. So there's symmetry with these lone pairs. And so one lone pair essentially cancels out the other. Same with, so 2 lone pairs on here, or if I switch to this is the other one. So it's really these two situations when the lone pairs completely cancel out. So this would be AX2E3. The electron geometry is trigonal bipyramidal. Molecular geometry is going to be linear. And the other one was square planar. So you've got these even lone pairs. So one of them is AX4E2, and the other one is AX2E3. So an example of uneven lone pairs be like water. All right, so we just saw water just based on these bonds is going to be polar, but also because these electrons are on the same side of the molecule, that also makes it polar. So look for the lone pairs. And then if you have different atoms, so here it says all the atoms are the same or have the same electronegativity, really the only time you need to check is if you have a different atom in the mix. So if it was CH3F. So in this case, I don't have any lone pairs on the central atom. But fluorine is going to have a different electronegativity than hydrogen. So that would be polar. Okay, so let's go look at these two real quick. So a molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? Would all 3 of those fluorines cancel each other out? They would. Do I have any lone pairs? Around the fluorines, yes. Around the central atom, no. So a complete Lewis structure would be nope. I think it's this trigonal planar that's maybe the hardest to think about in terms of like how those cancel out. We essentially have 3 vectors like that, and so this one's going to have some component that way, which gets canceled out by that one. These ones have combined components here, whereas this one just has the full component like that. And then depending on how accurately I drew my arrows, which apparently not very accurately, the magnitude of these two combined should cancel out the downward of that one. Yeah. Yes. Put hydrogen there. Now this hydrogen, the bond polarity would be, wait, let me try and draw it to scale. I would have these two like that, and then they'd be trying to cancel out this little tiny baby arrow. Net movement in that direction. Okay. So these are the most common ways that you get polarity or nonpolar. So like tetrahedral, if they're all the same, it's nonpolar. It's another one that's hard to see with the vectors. The trigonal planar is going to be nonpolar, again, if they're all the same. Right, and both of this one doesn't have any lone pairs. This trigonal planar could be a trigonal planar from the, it couldn't be. I'm thinking square planar. It's like a square planar, if I've got lone pairs on either side, those cancel out. Trigonal planar wouldn't have any lone pairs. Bent has lone pairs, it's polar. Trigonal pyramidal has lone pairs, so it would be polar. So most of the time, if you have lone pairs, they're polar, unless there's lone pairs directly opposite each other. All right, yeah, I think that's basically it for polarity. This is the reason that like things like oil and water don't mix. I actually bought some magnetic marbles for once, but they were cheap and they suck. They don't work very well. I was like, it'd be really cool to have the marbles together because the magnetic marbles stick together because they've got magnets in them and they've got this attractive force that holds them together. So if you shake up a bunch of them, which is what's happening all the time inside of a liquid, these would tend to stick together while these non-magnetic marbles would eventually get pushed out. They wouldn't get back in because they're not magnetic. So that's the reason that oil and water don't mix. The water molecules like really hanging out with other water molecules, and the nonpolar molecules just don't care. So they just float to the side. So then you need something like soap if you want to make them mix, because it's got both. It's polar on one end, it's nonpolar on the other end. So the nonpolar end gets into the grease and acts like an anchor. And then when you wash water over it, the polar head gets stuck in the water and then drags the grease along with it.